Hello everyone, welcome to OPAM filter topic. Today we are going to see the summary for OPAM filter concept and design. So here before we begin, there are some acronyms. So BPF stands for band pass filter, HPF stands for high pass filter, and LPF stands for low pass filter. Henceforth we will be using the short forms. So we have divided these OPAM filters into 8 short lectures starting from 41A, B, 41C, D, E, F, G, and H. So we have lectures, total of 8 lectures, which we have divided this, which will complete the entire module of filter topics, that is OPAM filters. So today we are going to briefly start with lecture number 41A, and we are going to briefly introduce the filters with example, explain what is the difference between the active and the passive filters, then what are the different types of filters and the ideal responses, and then we will study the passive, we will see the circuit for the passive first order, low pass filter, high pass filter, and band pass filter. We will simulate its frequency response in LT Spice. So those are the contents for the first lecture in the series 41A. Okay, so let us begin. Okay, let me put it in the full screen mode. Okay, yeah. So this is lecture number 41A, and we are going to start with the active filters. So basically, what are filters? Here there are some points written. I don't want you all to read. I'll just describe these points. So basically, the filter definition is as follows over here. Let me use the annotation button and highlight a certain text. So you can concentrate on this paragraph. Okay. Let me clear and let me add one more time. Yeah, so look inside this box. This is what we will be doing it right now. So RC active filters is a frequency selective electrical circuit that passes electrical signal of specified band of frequency and attenuates the signal of frequencies outside the band. So this is what we call it as a electric filter. Let me just highlight these points. Color I will be using red. Okay, so a frequency selective electrical circuit that passes electrical signals of specified band of frequencies and attenuates the signal of frequencies outside this band. Now this is called as electric filter. Okay, so that's what the electric filter means. And these electric filters may be analog or digital in nature. So we are going to focus on only on analog filters in this subject in OPAM filters. We will be focusing only on analog filters. So again, I repeat, electrical filter is the one is a frequency selective circuit that passes signal of specified band of frequency and attenuates signal of all the other frequencies outside this band. Okay, so let me clear this out and let me close the annotation. Yeah. So now it is better. So the simplest way to make a filter is by using passive components, that is RLNC. So this RLNC will work well for higher frequencies or radio frequencies. But at audio frequencies, what happens? So for audio frequencies, the inductor becomes problematic because the inductors becomes large and expensive because the inductor value have to be large for higher frequencies. So if you all know that, let me just write something over here. Okay, so we all know that XL is equal to 2 pi FL, or you can call it omega L. So as the frequency increases, as your omega increases, your XL will also go on increasing. So basically your L has to also will has to be of a higher value at low frequencies, basically. Okay, so that's what the reason is. We don't use a passive filter at at lower frequency. So for low frequency application, we will be requiring we will be have to look out for the solution for in place of an inductor. So the solution over here is, let me just okay. So the solution over here is the active filters. So the active filters will overcome the above mentioned problem of passive filters. So the active filters will use, let me just again highlight. Let me use a color as red. So the active filters will use your active element as op-amp, and they will use a resistor and capacitors as the passive element. So basically, active filters will be containing an active element in the form of a op-amp, and they will be containing resistors and capacitors only in the form of passive elements. Okay, so that's what it is. So we will get an inductorless active RC filters. Okay, and also there is a one very important point which we are going to discuss now. That is based on the, let me just, yeah. So op-amps, you know that if they are used in the non-inverting configuration, so if op-amps are used in non-inverting configuration, they offer high input impedance and low output impedance. Okay, so what this will do, this will improve the load driving capacity, and load is isolated from the frequency determining network. So that's why we use this. And also one last, that's why we normally prefer filters with op amps in working in the non-inverting configuration. Okay, because it offers very high input impedance and low output impedance, which will definitely improve the load driving capacity, and also the load will be isolated from the frequency determining network. Now, because of high input impedance of op-amp, large value of resistors can be used, thereby reducing the value of or the size of the capacitor required in the design. So we can play around with the resistor values, keeping the capacitor value intact. So these are the things which we can see. So this is a brief introduction of filters. Now let's move on to the next topic. Okay, let me stop the, yeah. Okay, so now we'll study the type of filters and their ideal responses. Okay, so active filters also have some limitations. So the high frequency response is limited by the gain bandwidth product and the slew rate of op-amp. So this is also very important. This is one of the limitation of active filters using op-amp. So the high frequency response will be limited by the gain bandwidth product, which is around 1 megahertz for 741, and the slew rate of op-amp. Okay, and moreover, the high frequency active filters are a little more on the higher side on the cost than the passive filters. So for passive filters, if you want to have a high frequency filtering, you go for passive filters, and if you want to moderate to low frequency filters, you go for active filters. Okay, so what are the types of filters? So the types of most commonly used filters are low pass filter, high pass filter, band pass filter, and band reject filter. Now, band reject filter is also called as band stop filter. It has a third name also. It is also called as notch filter. Okay. Now let us see them one by one. So the characteristics, if you see over here in point number A, over here, which you see, it is the gain versus frequency. Basically, it's a frequency response, right? So what do you see? Concentrate on the dotted line. So frequencies below fh will be passed, and the frequencies above fh will be attenuated, right? And the actual response will be looking like this. It will be constant for the pass band, and slowly it will keep on attenuating after frequency fh. Okay, and once it passes the band in which the frequencies are passed are called as pass band, and the band at which the frequencies are attenuated is called as stop band. Okay, so this is my ideal and the actual frequency response for a band sorry, for a low pass filter. It's basically a low pass filter. Why? Because it will pass all the low frequencies less than fh. So all the frequencies lesser than fh will be passed over here. and all the frequencies above fh will be attenuated. Okay, let's come to the diagram number B. Now this is the diagram for a high pass filter. So this is the frequency response. Basically, as you can see, at frequencies lesser than FL, all the frequencies are attenuated, and at the higher frequencies, it will pass all the higher frequencies, right? And the band in which the frequencies are passed is called as pass band and stop band. So here, if F is greater than FL, that is the pass band, and if F is less than FL, that is called as the stop band. Now, similarly, the third part, the C part, is of a band pass filter. So basically what it will do is it will pass a band of frequency. Let's consider the audio frequency. So let's say the audio frequency is from 20 hertz to 20 kilohertz. And I want to design a filter which will pass only the frequencies between 20 hertz to 20 kilohertz. Let me use the annotation now. So let's say I have over here 20 hertz is my audio frequency, right? So this is 20 hertz, and over here I require 20 kilohertz. So this FL will be 20 hertz, FH will be 20 kilohertz, and my pass band will be like, I want to pass the audio frequency only between 20 hertz to 20 kilohertz. So for such type of filters, for such type of response, this is called as a band pass response. So basically, it will pass a band of frequency. So what are the frequency ranges? So in this example, 20 hertz to 20 kilohertz is the frequency range. And if any frequency is below 20 hertz, we want to reject it. So that comes under the stop band. And if any frequency is lesser than, if greater than fh, that also will be rejected. So only the frequencies between the fl and fh, that is 20 hertz and 20 kilohertz, will be passed as per the response of a band pass filter. Now this is my actual response. Ideally it looks like a step, as you can see. So between FL and FH, it will pass all the frequencies, and below FL and above FH, it will not. It will attenuate the frequency. So there are two stop bands and one pass band in case of a band pass filter. Okay. Now let me clear out the drawings. Okay. So the last category of the filter is the band reject filter or the band stop filter, or also called as a band notch filter. So as you can see, it's exactly reverse of the earlier band pass filter. So over here, it will reject a single frequency. Okay. So it will reject a single frequency. Let's say we want to reject a frequency, let's say F naught. Okay. Normally, when we do the design biomedical applications, we have to remove the 50 hertz noise. So basically, let me annotate it. So basically, this frequency, let's say you want to remove 50 hertz frequency, right? So you design a single frequency of 50 hertz. So you need to design a band reject filter. So let's say you want to reject, let's say 49 to 51 hertz. So it can be a range of frequency which you want to reject, right? Or it can also reject one particular frequency, that is 50 hertz. Okay. So here in general case, it will reject the range of frequency. So here I can write it as, let's say, 49 hertz. Okay. And here I can write it as, let's say, 51 hertz. So I want to reject the frequencies 49 to 51 hertz, and I want to pass all other frequencies other than this. Okay. So for this type of filter, we use a band reject filter. So it will reject the frequencies which are between FL and FH, whereas it will pass all the frequencies other than this range. So this band reject filter has two pass band and one stop band. Okay. And we have this ideal response, and this is my actual response of a band reject filter. Now let me clear out the drawings and close the annotation. Okay, fine. I hope that you got a clarity over what are the types of filters and what are their ideal responses. So the first one was a low pass filter. This one is my high pass filter. The third one was the band pass filter, and the fourth one is the band reject filter. Now let us go to the next one. Okay, I guess I have to little bit go to the next slide. Yeah. So let's revise these filters again. So they are very important class of electronic circuit, as we have seen. Let's consider this. Let's understand the concept of filters, why they are required with the help of example. So let's say you consider three signals V of t. So V of t consists of V1 of t and V2 of t, let's say. And V1 of t is Vm1 sine omega 1t, and V2 of t is Vm2 sine omega 2t. Okay. So let's consider that V1 of t is of higher magnitude but low frequency, and V2 of t is of lower magnitude but higher frequency. So again, I repeat, V2 is a high frequency signal but low amplitude, and V1 is a high amplitude signal but low frequency. And if you merge them together, let's say I want to add the low frequency and the high frequency component together. So the output which you will get is this. So this is my resulting waveforms. Okay. Sometimes whenever we take the data from the sensors, the data from the sensors is available in this form, directly V of t. And from here, we have to extract the original signal, the low frequency component and the high frequency component. Actually, that is the main use of the filter. So this filter, from this output waveform, it will give you back the low frequency and the high frequency signal. So actually, it's the reverse process. Okay. So let's pass this V of t. Let's pass this output to a low pass filter. So if you pass this output to a low pass filter, the output should give you the V1 of t at the output. Correct? So what is the action of a low pass filter? So low pass filter with a cutoff frequency omega c between omega 1 and omega 2. So you see omega 1 is the frequency, is the low frequency, and omega 2 is the high frequency. So between omega c, that is between omega 1 and omega 2, it will pass the low frequency component, which is consisting of V1 of t, and it will remove the high frequency component. Okay. Now that is what it will do. So basically, this is the nature of the waveform which are most found in the nature. It may consist of more than one frequency, and we want to filter out the some frequencies, and we want to pass only, let's say, low frequency or high frequency. Okay. So if such output is passed to a low pass filter, the output of the low pass filter will give you V1 of t. Okay. So that is what is exactly happening over here. Now, next, okay, before going there, let us observe this thing in the LT spy simulation. Okay. So this is the simple filter concept which we are going to see now. So V1 is of low frequency with amplitude 1 volt peak to peak, and V2 is the high frequency component. That's what I was about to show you all. So let me simulate this. So this is my V1, which is the low frequency component, and this is my the high frequency component, and that's my output. The green color one is my output, which is the combination of this blue color and the red color. So the red color is my low frequency signal, my blue one is my high frequency signal, and my green one is my which is a combination of this low and high frequency. So if you pass this green color waveform, let me just divide this into frames. Okay, if I pass this, I mean, many analog signals may be this kind of a nature. If I pass this to a low pass filter, I will get V1 of t back. So that was the concept which was explained in the PDF. Okay, this was what explained, and this is what I have drawn over here like this only. So this is exactly what it means. Okay, so this green color signal is containing a low frequency signal as well as a high frequency signal. Now let us move forward. Now let us look at the transfer function of a low pass filter, which will be the ratio of the output to the input of the low pass filter in detail, slightly details. So we will discuss this in ideal filter domain only. So again, I'm repeating over here. Let me just put it in the full screen mode. Okay. Okay, it is in the full screen mode now. Okay, just a wait. Okay. So the ideal filters are the ones, ideal low pass filter are the ones which will pass all the frequencies below omega c, but it will reject all the frequencies above omega c. And h of j omega is the transfer function of this low pass filter. Omega is the angular frequency in radians per second. Omega c is the cutoff frequency. So what's mathematically, how will you write? If omega is less than omega c, then h of j omega is equal to 1. This is the normalized value. Okay, normalized value of the gain. That means the low pass filter passes all the frequencies up to omega c, and when omega is greater than omega c, then h of j omega, that is the gain, is 0. That means it will reject all the frequencies. And yeah, and that means that low pass filter rejects or blocks the frequencies higher than omega c. Okay, so that's what will happen. So now we'll come back to a same example. So you remember V of t was V1 of t plus V2 of t. So V1 of t was low frequency component with frequency omega 1, and V2 of t was high frequency component with frequency omega 2. Now if we apply V of t to the low pass filter, the output will be V1 of t. Okay, so that is what will happen. So we will have an output which will be equal to the low frequency component, whereas the high frequency component will get rejected. Only the low frequency component will get passed. So this is what the concept is of a filter circuit. I hope that this is clear. And similarly, we can define the high pass filter response. As you can see, this is the ideal response of a high pass filter. You have again h of j omega as the gain, and you have omega c, which is the cutoff frequency for a high pass filter. And h of j omega is basically the transfer function, the gain of the system. So over here, mathematical, how will you define? So over here, for omega greater than omega c, h of j omega is 1. That will, the frequencies above omega c will be getting passed. And if any frequency omega is lesser than omega c, h of j omega will be 0. That means frequencies below omega c will be rejected. Okay. So high pass filter with a cutoff frequency between omega 1 and omega 2 will pass the high frequency component. Let us come back to our example. Our high frequency component was V2 of t, and will remove the low frequency component. So if the same V of t, which was consisting of high and low frequency, is passed to a high pass filter, the output will be V2 of t. Remember, V2 of t was containing the high frequency component. So yeah, so the high frequency component will be passed, and the low frequency component will be rejected by this high pass filter. I hope that this point is clear. Now, third is the band pass filter ideal response. So this is the ideal response, just like a step. Okay, let me just go back over here. So okay, so it has actually, I should have written the pass band and stop band also. So here in between you have your pass band, and above and below, this is my stop band. Here also is my stop band again. So the band pass filter will pass a band of frequencies between omega L and omega H. It will reject all the other frequencies. So mathematically, how will you write? So between omega L and omega H, h of j omega will be 1, and below omega less than omega L and omega greater than omega H, it will be h of j omega will be 0. So that's the ideal response. Similarly, band reject filter will be exactly reverse. So it will reject the frequencies between omega L and omega H, and whereas all the frequencies will be passed. Now, these are all ideal frequency responses of the various filters. So again, I repeat, there are 4 types of filters: low pass filter, high pass filter, band pass filter, and band reject filter. So all the above filters are ideal filters which are not practically realizable. So in real life, we'll approximate the ideal behavior and approximate the ideal behavior of the filter with the help of mathematical function, and implement them using circuits. So from now on, your journey of your active filter starts. Okay. Okay, so we will be discussing few passive filters before moving on to active filters quickly. So this will be a quick revision. So let us look at how the filters can be implemented in practice. Let's say a RC passive filter we want to build. So let's say this RC combination over here. We are applying a AC supply. We have a R value of 100 ohms, C value of 5 microfarad. So what will be the transfer function of this? The transfer function of this will be V of t, V of S upon V S of S will be, so H of S will be 1 upon SC divided by R plus 1 upon SC. Okay, and here we can write the same thing as 1 divided by 1 upon S upon omega 0, omega naught. So this is my first order polynomial. Okay, and with omega naught is equal to 1 upon RC. So F naught will be 1 upon 2 pi RC. Correct. So if you calculate with a calculator, this number F naught will come out to be 318 hertz. So it will be 1 upon 2 pi RC. So please substitute this value. F naught will be 318 hertz. Okay. So I told you all that practically you will not get a ideal response. You will have a actual response which is looking like this. So if you plot these values with the different frequencies and the gain in dB, if you calculate, you will plot this frequency response. Before we have covered how to plot a frequency response when we were discussing differentiator and integrator. So you can follow a similar approach. But right now, if you want to check, so around 318 hertz, any frequency below 318 hertz will be passed, and above that the frequencies will be rejected. The gain will keep on reducing at the rate of 20 dB per decade. So here, since it is a first order polynomial, the order of the filter will be one. So basically this is a first order low pass filter. Okay, and this is also called as a roll off rate. So the rate at which the gain falls per decade change in frequency is called as roll off rate, and here it is for a low first order low pass filter, passive filter, it is minus 20 dB per decade. Okay, now let us check this out in LT Spice. Okay, let me keep this open and I'll open up the LT Spice window and I'll close this and open a simple low pass filter response, passive first order. Yeah, so that's example of a passive first order low pass filter. And R1 value, acha, okay, we have taken a different value, not a problem. We can take a similar value to this. Let's take a similar value. Okay, so R1 was supposed to be 100 ohms and C was supposed to be 5 microfarad. Okay, and we have applied AC of 1. Let's check the frequency response. Okay, so if I click over here, this will give me the frequency response directly. Okay, and this plot the phase and the magnitude plot. Let's remove the phase plot. So over here, okay, as you can see clearly, this is the exactly the same thing which we have got over here. Let me just slightly reduce it so that this is clear. As you can see, if I plot the frequency response for this RC circuits, which is a first order passive low pass filter, I will get this type of frequency response. Ideally, it should be like a, it should pass all the frequency immediately, but it will take some time. So how will you measure the cutoff frequency? Go 3 dB down. This is 0 dB, so you have to go 3 dB down. So it will be around minus 3 dB. So if I go a little bit down, okay, I will push this over here. So exactly around 3 minus 3. Okay, this is minus 3. And as you can clearly see, the value is 318.06 hertz. And that's the same value we got it from the calculation. Okay, so that's what is happening over here. And one more point was made that it reduces the roll off rate is 20 dB per decade. I mean the minus 20 dB per decade. You can check that. If you check the frequency at 1 kilohertz, it's around minus 10 dB, minus 10.5, and around 10 kilohertz, it's around minus 30.05 dB. So you can see that there is for 1 decade change in frequency, the gain falls by a rate of minus 20 dB per decade. So this is a classic example of a low pass filter. So what it will do is it will pass all the frequencies. Let me just get back to that minus 3 dB. Okay, again it has gone. Let me adjust this to minus 3. Yeah, this is minus 3, right? So over here, as you can see this line over here. So about this, I mean to the left hand side of this line, I mean all the frequencies before the 318 hertz will be passed as it is. And if you try to pass any frequency beyond this 318 hertz, it will reject it and the gain will keep on drastically falling down. Okay, so that's a classic example of a low pass filter. It will pass all the low frequencies, okay, and it will reject all the frequencies above 318 hertz. Okay, so this filter will pass all the frequencies up to 318.14 hertz. So that's the classic example of a low pass filter. Now let's quickly see a high pass filter on a similar manner. So let's say we have a high pass filter. So how will be the transfer function? Transfer function will be R divided by 1 plus S into C. So you will get this form SRC upon 1 plus SRC. Here you take S upon J omega divided by 1 plus S upon J omega, wherein omega naught will be 1 upon RC. This is a first order polynomial. See, I'm not going into detail because this is a passive filter. I just want you to give you a feel of how does the filter response will look like in passive also. Okay, I think the frequency is wrong over here. We have to recalculate it. So here, let me search for a calculator. Okay, so I am guessing that this number might be close to 318 hertz only. Let's check it out later. Yeah, it might be close to 318 hertz. So here is my oh yeah, f naught will be omega naught upon 2 pi. So here also the order of the filter is 1. So it's a first order high pass filter. And how logically you will think. So in case of a low pass filter also, I mean, if you don't do analysis, what do you logically think? So for frequencies very less close to zero, what will be the reactance offered by the capacitance? So the reactance offered by the capacitance at frequency equal to zero will be almost infinity. Correct? Xc is equal to 1 upon 2 pi Fc. Correct? So at low frequencies, the capacitor will behave as an open circuit. So all the signal will be passed from output, from the input to the output. And as the frequency increases, the reactance offered by the capacitance goes on decreasing. And as you can see, if it goes on decreasing, the gain will go on reducing. Okay, as you can clearly see over here. Similarly, for a high pass filter, for low frequencies, the reactance offered by the capacitance is infinity. So it will be like open circuit. So hardly any input will reach the output. And as slowly the slowly if the frequency increases, the reactance offered by the capacitance goes on decreasing, and slowly the frequencies will be passed. Okay, so if you consider this transfer function, and the cutoff frequency will be 318 hertz, and this is how the frequency response will look like. It's like a high pass filter, so it will pass all the frequencies above 318 hertz, and it will stop all the frequency below 300. It will reject all the frequency below 318 hertz. So this is my stop band. Below f naught is my stop band, and above f naught is my pass band. Okay, and let us check this out. And the slope over here is plus 20 dB per decade. Okay. Okay, fine. Let us check this out in LT Spice. So I have to open the circuit for a high pass filter quickly. Okay, this is a high pass filter. I will run it and check the frequency response directly. So as you can see, as predicted, the frequency response is exactly of the same nature, as you can see. And now if you want to check the cutoff frequency, it will be around 3 dB down. So I have to adjust exactly equal to 3 dB. So let me do that. This is 3 dB. So minus 3 dB down, the value of the frequency is 319 hertz, which is very close to 318 hertz, as you can see very clearly. So below this frequency, that is, if any frequency below 319 hertz will be rejected by this high pass filter, and all the frequencies above this 318 hertz will be passed by this band pass, by this high pass filter, as you can clearly see over here. Okay, I hope that there are no doubts now in this. Let's quickly check the next one now. Okay, so actually this is what we have carried out already, high pass and low pass filter. There is a concept called as a passband gain. In this filters, the passband gain is 0 dB. So this is my passband, right? What's the gain over here? As you can clearly see over here, the gain is 0 dB. Okay, so we call it as a passband gain. Passband gain over here is 0 dB. 0 dB means gain of 1. Okay, that is a normalized gain which we have took. That's why there's information about passband gain is written. Okay, so we have already seen its response. Okay, and similarly we have a band pass filter. So you see a band pass filter, it's a passive filter, right? So it will have three elements, R, L, and C. And I'm not going into detail about the transfer function. So transfer function will be SL parallel to 1 upon SC divided by R plus S into L parallel to 1 upon SC. If you simplify it, you will get this S into R by L divided by 1 plus S into R, L by R into S square L into C, with omega naught is equal to square root of uh, square root of LC. So F naught will be around 7.96 kilohertz. Okay. And this will be the band pass frequency response. So if we can work it out in a calculator, you will get this. So it will be S square, omega naught square. Okay. This is my R, L, and C. Elements all three are present. That means it's a passive filter, passive band pass filter. And it will pass the omega naught will be close to around 7.96 kilohertz. Okay. It will be a very narrow band pass filter. So the above circuit will pass the frequencies around 7.96 kilohertz. Okay, the small band of frequency which will pass, and it will reject all the other frequencies. So let's check this out in LT Spice. I guess I have the circuit with me. Let me check it once. Yeah, band pass filter, I have it. So we can take the same values over here. 0.1 millihenry, C is 4 microfarad, and R is 100 ohms. So let's check the response of a passive band pass filter. Yeah, as you can see clearly, it passes a band of frequencies, and let's check this value. This value should be close to around 7 point something, right? Yeah, it should be close to 7.96, and we are getting ridiculously close value. Okay, I need to move it a little up. Yeah, so if I expand it further, if I can take this up, yeah, as you can see, the upper peak, the highest peak will be over here, 7.94 kilohertz. Okay, so it will pass a small, as you can see clearly, the frequency response looks exactly the same way. So you have a small pass band over here. This is my pass band. So nearby around 7.94 kilohertz frequency range, a small pass band is there, and that frequencies are getting passed, whereas all other frequencies are getting attenuated. So this is the norm. This is actually a narrow band pass filter. So very narrow range of frequencies are passing. So if you come 3 dB down, only those range of frequencies are passed. Yeah, I think I have to adjust this properly. So let me make it a little bit more clear. So here it is -3, and here I'll take another one, and I can pass it over here. Okay. So what is the range of frequency it's passing? It's passing frequencies between 7.39 kilohertz to 8.6 kilohertz. That's a very narrow range of frequencies which we are passing over here. Okay. I hope that this point is clear. Now let us go to the PDF. So we have seen the passive filter response for a low pass, high pass, and now band pass filter. Okay, so here is was a band pass filter. Okay, now let's come to the op-amp filter. So next lecture onwards, we will be starting with op-amp based active filters. So the op-amp filters can be designed without using an inductor. This will be a significant advantage because inductors are bulkier and expensive, and also it exhibits the non-linear behavior arising from the core properties, which is undesirable in the filter circuits. So with op-amps, the filter circuit can be designed with a passband gain. Okay, normally what happens is all these filter circuits which we have studied, I mean we have analyzed a passive filter, we can have a passband gain of 0 dB or 1, right? We cannot do more than that to adjust this passband gain, right? So wherein in case of your op-amp filters, let me go back over here. Op-amp filters, we can have a passband gain greater than 1 also. So a passive filter will have a passband gain strictly of 1, but active filter can have a passband gain greater than 1 also. And op-amp filters can be easily incorporated in integrator circuits because they don't contain an inductor. However, there are some situations wherein passive filters are still used. Now, passive filters will outsmart active filters at higher frequencies. So higher frequencies, op-amp does not work well. It has a very limited gain, and the high power which op-amp will cannot handle at high frequency, that is also another limitation. So these are the two drawbacks of active filters which we are going to see. Okay, so we have come to the end of this lecture. So in this lecture, we have covered the introduction to the filters with examples. We have seen the difference between the active and the passive filters. And then we have seen the 4 types of filters and the ideal responses. and we have simulated the seen the transfer function and simulated in LT Spice the frequency response for first order low pass filter, band pass filter, and high pass filter. I hope that this will serve as a strong base for studying the filter topic using op amps. So I guess that's it for this lecture. Next time we'll start with the first order active low pass filter circuit. So until then, have a good day and thank you.